Hello everyone. Today we will be discussing about the Unicast routing. Here, the first section introduces the concept of Unicast routing and describes the general ideas behind it. The session then describes least cost routing and the least cost trees. The second session discusses the common routing algorithm used in the internet. The section describes distance vector routing, linked state routing and path vector routing. And this section first describes RIP, that is Routing Information Protocol, a protocol that implements the distance vector routing algorithm. Then describes OSPF, Open Space Path First, the protocol that implements linked state routing. And finally, the section describes BGP, a border gateway protocol, a protocol that implements path vector routing. So, let us start with first the Unicast routing. So, what is Unicast routing? It is in the module 4 here. We'll be studying about this Unicast routing. Unicast routing in the internet with a large number of routers and a huge number of hosts can be done only by using hierarchical routing. Now, what is this Unicast routing is? As we know that the goal of the network layer is to deliver the datagram or the packets from source to the destination. If this packet or a datagram is destined for only one destination, we call it as Unicast routing, which is as simple as if the packet has to be sent to only one destination, then it is Unicast routing. Unicast routing in the internet with large number of routers and the host is done using hierarchical routing, that is routing in several steps using different routing algorithm. That is what we'll be studying in this. And in Unicast routing, what happens is packet is routed hop by hop from the source to the destination by the help of forwarding tables. Already we had studied about the forwarding tables. These are the switching tables or the routing tables. So here the source host or the destination host needs no forwarding table to forward a packet, but the routers that glue together the networks in the internet need the forwarding tables. So, routing a packet from the source to the destination means routing the packet from source to a destination router. So here, only the routers in the internet need forwarding table, routers that glue together the networks. The question is, what other routers the packet should visit? Here, we can see here the internet and its graphical representation. What happens here is that to find the best route, internet is modeled as a graph, which consists of a set of nodes and the lines or edges which connect the nodes. To model this internet as a graph, now each router itself is considered as a node and each network between the pair of routers are considered as an edge or the line. Now the internet is modeled as a weighted graph in which each line or each edge is associated with a cost. Here you can see that the numerical values, those are the cost here. If weighted graph is used to represent a geographical area, then consider it as some area, then the nodes can be the cities and those edges are the roads connecting the cities and the weights are the distances between the cities. So here we can consider that A and B are A, B, C, D, those are the different cities, and the weights that we have written are nothing but the distances between the cities. If there is no edge between the nodes, that means the cost is infinity. That means there is It is at infinite distance, both the cities. Assume there is a cost associated with each edge. Always assume that each edge there is a cost associated with it. So here we can see that the internet is modeled as a weighted graph consisting of nodes, which are routers, and the edges, which are networks, in which each edge is associated with the cost. Next, let us see about the least cost routing. When the internet is modeled as weighted graph, as we have seen earlier, one of the way to interpret the best route from the source router to the destination router is to find the least cost between the two. In other words, the source router chooses a route to the destination router in such a way that the total cost for the route is the least cost among all the possible routes. So, here the source router chooses the route to the destination router in such a way that the total cost for a route is the least cost among all the possible routes. It is something like between the cities, whichever distance is smallest, that is considered as the best route. So, in the example figure 20.1, which we have seen here, this is the figure. Here we can see that the weighted graph. Here, the best route between A and E, if you consider in this figure A and E, A to D to E is 8, A to B to E is 6. So, the best route between A and E is A to B, then B to E. That means the cost is 6. This means that each router needs to find the least cost route between itself and all the other routers to route a packet using this criteria. So, from each and every node, the router has to find out the least cost route, and in that route the packet should be routed. That is what the least cost routing is. Now, next we'll see about the least cost trees. So here, if there are n routers in the internet, there are n minus 1 least cost path from each router to another. Thus, we need n into n minus 1 least cost paths for the whole internet. That means, if there are 10 routers, we need 10 into 9, 90 least cost paths. All the paths can be combined together to form a least cost tree. So what is a least cost tree? It's a tree with the source router as the root that spans the whole graph, and in which the path between the root and any other node is the shortest. So distance between the path between the root node and any other node is the shortest. It is said to be the least cost tree. It is a tree with the source router as the root that spans the whole graph. That means visit all the other nodes. So here in the example, if you see A, B, C, D, E, F, G, these are the least cost trees for the nodes in the internet. So here, with respect, considering each and every node as a root node, here the distance from that particular node, it is the least cost path from that root node to every other node is calculated. That is said to be the least cost tree. And only one shortest path tree for each node and n least cost trees for whole internet. So here the figure shows 7 least cost trees for the internet. A, B, C, D, E, F, G. You can see here. So there are 7 least cost trees for the internet. that is n least cost trees for the whole internet and only one shortest path tree for each node. So here we can see from A to B, next A to D. These are the paths which are written with respect to the previous figure which we had seen. This one, A to B is 2 is the distance, A to D is 3 which itself is the least one. Next A to E, as we have seen, it is 2 plus 4. So A to B, B to E. Similarly A to C is A to B, B to C. Similarly continues. So you can see here A to C is 2 plus 5, 7. A to D is 3. A to E is A to B plus B to E. So it is 6. Similarly A to F, it is A to B plus B to E plus E to F. So 6 plus 2. Similarly F to G, it is 1, 8 plus 1, 9. So this is how, similarly considering each and every node as a root node, these least cost tree is constructed. So the properties of this least cost tree is that least cost root from A to F in A's tree is inverse of the least cost root from F to A in F tree. So if you consider the F tree and if you consider A tree, we can see that the least cost root from A to F, if it is 0 to 8, F to A is also, it will be 0 to 8. Similarly in other examples also. And second property is that instead of traveling from A to G using A tree, we can travel A to E using A tree and continue from E to G using E's tree. That is how we travel to A to G. That is about the least cost trees. Next we have about the routing algorithm. Several routing algorithms are designed in the past. The difference between these methods are in the way they interpret the least cost and the way they create the least cost tree for each node. So here we discuss some common algorithms. Later we see the routing protocols. So first one is the distance vector routing. It is very important. Even in the lab, a program is written, a C program is written to get distance vector routing. So this distance vector routing uses the goal we discussed in the introduction to find the best route. So here, in this, each node creates its own least cost tree with the rudimentary information it has about its immediate neighbor. The first thing that we should know in the distance vector routing is that here each node creates is its own least cost tree with the information it has about its immediate neighbor. And in distance vector routing, router continuously tells all of its neighbors what it knows about the whole internet. The incomplete trees are exchanged between the immediate neighbors to make the trees more and more complete and to represent the whole internet. That is what happens here. And we say that in distance vector routing, a router tells all the neighbors what it knows about the whole internet. Next is the Bellman-Ford equation and the concept of distance vectors are used in the distance vector routing. So let us first see about the Bellman-Ford equation. This is used to find the least cost and it is very important. By using this Bellman-Ford equation, the shortest distance is found out. This is used to find the least cost between the source node X and the destination node Y through some intermediary nodes A, B and C. You can see in the diagram here, general case is shown. So when cost between the source and the intermediate nodes and the least cost between the intermediate nodes and the destinations are given. So here To find out the distance here, we consider the minimum of the distances, and then we write down the minimum distance is the distance between x and y. And also we can see the below diagram. If dxy is known, then if there is one more new route cxz to dzy, and if that is minimum, then once again the path is updated. That is a Bellman-Ford equation. Next is the general case in which here we can see that dij is the shortest distance and cij is the cost between the nodes I and j. Next is this Bellman-Ford equation enables us to build a new least cost path from the previously established least cost path. Next, the second thing that we should know before going to the distance vector routing algorithm, along with the Bellman-Ford equation, we should be knowing distance vector. So distance vector, a least cost tree is a combination of least cost path from the roots of the tree to all the destinations, and these paths are graphically glued together to form tree. The distance vector routing creates the distance vectors which are one-dimensional array which are used to represent this least cost tree. Whatever we have seen the least cost tree, the same thing is represented as a one-dimensional array using the distance vector. So the name of the distance vector defines the route, which will be written above the one-dimensional array. Indexes, which will be written inside, these define the destinations, and the contents inside that array, the value defines the least cost from the route to the destination. So remember always that distance vector does not give the path to the destination as the least cost tree does. It gives only the least cost to the destination. It will not tell about the path. It gives only the least cost to the destination. How each node in an internet originally creates the corresponding vector. Here you can see that this is a tree and this is a distance vector. So here, considering a root node as A, to all the other nodes the distances are tabulated here, and these are the, using the Bellman-Ford equation, these are the minimum of the least cost distances. Now, how each node originally creates the corresponding vector. You can see here each and every node vectors are shown. So each node in the internet, when it is booted, creates a rudimentary distance vector with the minimum information the node can obtain from the neighborhood. The node sends greeting messages out of its interfaces and discovers the identity of the immediate neighbors and distance between itself and each neighbor. It then makes a simple distance vector by inserting discovered distances in the corresponding cells and leaves the value of the other cells as infinity. Here, these rudimentary vectors cannot help the internet to effectively forward a packet. Here what happens is that the vectors are made asynchronously when the corresponding node has been booted. So these vectors cannot help the internet to forward a packet. The nodes in the internet need to help each other by exchanging the information. After each node has created its vector, it then sends a copy of the vector to all its immediate neighbor. And after node receives the distance vector from neighbor, it updates using Bellman-Ford equation. However, we need to understand that we need to update not only one least cost but n of them, in which n is the number of nodes in the internet. So here you can see that here node A thinks that it is not connected to node G because the corresponding cell shows infinity. To improve this, nodes in the internet need to help each other by exchanging the information. These are with respect to the node, considering those respective node as a root node. These are the least cost trees which are represented in the array form, which is nothing but a distance vector. This is the figure, and these are the distance vector corresponding to those nodes, considering that particular node as the root node. So which is directly approachable or directly connected, those will have the value. Which cannot be connected directly, like with respect to B, D cannot be connected, F cannot be connected, G cannot be connected directly, then those will have the value as infinity. Next is updating the distance vectors. So here we can see that in the figure there are two events shown. Those are the asynchronous events. So the vectors are made asynchronously when the corresponding node has been booted, which was told. So here there are two asynchronous events happening one after the another with some time in between. You can see here. So in the first event, node A has sent its vector to node B. You can see that node A has sent a vector to node B, and the node B updates the vector, and we will have from the old B the updated new B. So here from the distance between A to B, we know that the distance between A to B is 2. Now here with respect to the old B, this is used to get the event as using the cost from B to A as 2, we will be updating the distance of B to D. So let us see this figure. To get the distance from B to D, initially we can see that in the old B, B to D is infinity. So you can see from B to D is infinity as we cannot directly connect it. So what we do is we take the help of A. So when we look at A's table, we'll get to know that the distance from A to B is 2. And also distance from A to D is 3. So as we already know that distance from B to A is 2, or it is A to B is 2. So to get D, if we go from A to D, which is 3, we can reach B to D. So the new value from B to D will be 5. That is what will be updated. You can see here, new value from B to D is 5, which is obtained by taking old B, which is added with 2 plus A. So 2 plus old A and B, whichever is minimum, will get the new B. That is one event. In the second event also, the node E has sent the vector to node B. You can see here, node E has sent a vector to node B, and the node B updates the vector by using E. So here we can see that in the earlier, from B to reach B here, which is the old one, using E it updates. So using E it can go to D, also it can go to F. D has already reached with the minimum path, it can reach F now. So you can see that in the B's table or B's distance vector, you can see that the F value, that is the distance from B to F, is infinity. But as we cannot connect it directly, but using E, we know that the distance between E to F is 2. So we know the distance from B to E is 4, So e to f is 2. Once we get e to f is 2, it will be updated, and in the updated distance vector of b, the distance between b to f will be changed from infinity to 6. That is what it tells. So here it should be CEB, which is equal to 4. So here it takes that value which adds along with the old b's value. So old b value was infinity. So using b, how to reach f? Using e, how to reach f from b? That is what is shown here. Here also from b using a, how to reach d, that was shown. So this is what the updating is. After updating, it immediately sends the updated vector to all the neighbors. So this is about the distance vector. So we have seen here in today's class, we have discussed about the construction of the least cost trees, and also we have seen about the distance vector routing algorithm. To explain that algorithm, we need Bellman-Ford equation and concept of distance vectors. So it is explained, and also we have seen about the distance vectors, and also with the example it is shown how the table gets updated as in when it receives the forwarding tables. In the next class, we'll continue with the distance vector routing algorithm, the problems associated with it, the solutions, and also the link state routing algorithm. So, thank you.